Good afternoon, everyone. My name is Alexa Limon Bonilla, and I'm studying a bachelor's degree in biotechnology at the Universidad Autónoma de Puebla. And today I'm going to talk about some of the interesting characteristics about indium phosphide quantum dots. In the last 2 decades, the synthesis of semiconductors nanocrystals has opened a possibility in the design of new materials or devices with unique optical, electrical, thermal, and biological properties. One of the main areas of scientific interest is to generate new applications with the quantum dots, such as photoluminescent devices, diode lamps, screens, photodetectors, photovoltaic devices, solar cells, and biological markers. About the experimental details, is that our synthesis was a one-pot method in which we put all the precursors in one phase, but for each sample, the use of the myristic acid was increased, as we can see in Table 1. After the synthesis, we obtain our colloidal quantum dots that we can see in Figure 3 under UV light, highlighting its photoluminescence. For the last step, that was our setup, we deposit the quantum dots on Corning glass to determine their characteristics. And now, as a result of all this experimentation, we have the characterization of the quantum dots. First, as we all know, the X-ray diffraction analysis is useful to analyze the structure of materials, and as we can see in our diffractograms, it was possible to identify the presence of indium phosphide, indium oxide, and zinc sulfide. And maybe you're wondering why is the indium oxide in there, and I'm going to tell you why. When we go down in our samples, the myristic acid increase and the indium phosphide does too. And this is because the interaction of the myristic acid and the indium acetate because it produces oxygen and in result indium oxide nanocrystals. Moving on into the XPS analysis, the details of this technique confirm the X-ray information, and we can also observe the formation of indium oxide but in a low level. This is about the thing that I mentioned previously about as we go down on samples, the myristic acid increase and therefore the indium oxide. And as we were talking about sample number 3, this is why it's a low level of indium oxide. Now, in order to determine the absorbance, the band gap, and the particle size of our quantum dots, we use UV-Vis and the equation of the Bohr exciton radius. And we have to consider that the semiconductors like indium phosphide, the value of the Bohr radius is about 9.8, and as we can see, the highest value for our sample number 7 is 9.8 nanometers, so that means we're going on the right way. In addition, we have the photoluminescence spectra that is used to study the optical properties of materials. We know that when materials absorb photons and then re-emit them, this process is known as photoluminescence. So, our photoluminescence spectroscopy shows us that the samples 7 and 8 exhibit the highest luminescence, reaching a maximum of 2.43 and 2.85. But talking about specifically the sample number 8, this is not the best because of the different peaks that the graph shows. This is explained a little better with the technique of time resolution photoluminescence because in here we can determine if our sample have radiative or no radiative phenomena. So here for sample number 2 we can see that the non-radiative phenomena are the one that predominates. So that means that our sample we have to go to many steps before being able to emit a photon. And this, talking about application of photoluminescence, is not very useful because it will take too long to do its job. But important thing here is that we don't have the samples in here, but the samples that have a core shell, when they have a core shell, the indium phosphide bonds are complete and the radiative phenomena will be present. Finally, Thanks to these results, it was possible to use quantum dots in different types of applications, such as biomarkers, solar cells, devices, screens, cameras, and many others. Thank you for your attention.